Okay, hello again. This lecture will be different from the rest of them in that what we'll do now is actually apply all the knowledge that we've gathered in the previous two terms to try and simulate a simple spin system. Now, we'll not be using any standard software, we would not be using anything that's been pre-cooked or pre-made. Here's the blank screen in front of me with MATLAB editor open and just an empty file. So what I'll do now is guide you step by step from this empty file to a simple two-spin simulation of a J-coupled spin system. And hopefully this will put things into context, because it is usually quite hard to get from fairly abstract notions that we've been developing, the Lie algebras and such, into the practical context of how to actually do these things. So what I'll do is just type with comments a simple two-spin simulation here. Right, if you haven't encountered MATLAB before, it's a pretty simple system for practical purposes. I wouldn't explain the syntax, I'll just type it. The syntax is fairly self-explanatory. What's important actually is that when we write the code, that we do not leave to the last stage the documentation of it. Trust years of experience of writing things like spinach. If you do not put comments into the code at the time you're writing it, you'll never have time to do it. It'll just remain uncommented and it'll be an absolute nightmare then to read it. The same applies to clarity of writing. It is imperative that things be given descriptive names. If something contains a Hamiltonian, call it Hamiltonian, or at the very least H, if it's a standard notation. Call all functions something descriptive and put copious comments into what you're writing. So, in that spirit, the first thing we'll write is the comment. Simple two-spin simulation program. And it's usually a good idea to put a list of contributors, the people who put an effort into writing the code. If you are going to write something big, it will inevitably be several people who would write that, and so at least their emails are usually a good idea. Okay, and so function hello world without any input parameters. So the first thing we need to do is to set up the very basic infrastructure. And the very basic infrastructure in an SU2 Lie algebra is the three Pauli matrices. So define Pauli matrices. And well, we just define them as we usually do. Typical notation is sigma, so sigma x equals just a definition of a matrix, 0, a half new line for a matrix, a half 0, a semicolon to suppress the actual output, otherwise it will print to console at runtime. Then sigma y is, as the textbook says, minus 1i over 2. This is how I must be entered into MATLAB. Then 1i over 2, 0. That will be the sigma y matrix, and sigma z is similarly a half 0, 0, a half. Okay, so these are our matrices, and one other thing that is fairly useful and a good idea to do at any time that you're writing code is to not leave until the last stage the testing of what it is that you've written. It's pretty easy to make a typo or a mistake or something like that, and in a big code it's pretty difficult to catch. So it is often a good idea to just run cursory checks while you're writing that code as to whether things are correct. Well, here what do we know about Pauli matrices? We know that they commute in a certain way, in particular that sigma x times sigma y minus sigma y times sigma x is a commutator, and that should be I sigma z. So if we take a difference with z of I sigma z, then if we did everything correctly, what should happen is we should be getting a 0. Okay, so before I run this function, I'll just put an end at the end of it. And so what happens now is MATLAB defines our Pauli matrices and then computes the difference between the commutator and what it's supposed to be equal to. And I'll just find myself a directory here somewhere. Where to put it? Let's just create some directory on my very large disk in here. Teaching Southampton practicals, and save it there. So our hello world.m goes into there. So I'll get to MATLAB's main window, scale it into the size of the screen that's being recorded here, and get to the directory I have just created. Practicals. And yeah, there's our hello world, and if we did everything correctly, when we run it, we should get a 2x2 matrix of all zeros. So hello world. There we are, and something is actually wrong. You can see that the matrix is very definitely not a 0 matrix, and we have a 1 here. If I didn't test that, that error would not have been caught. So of course what's missing here is the minus on the sigma z, which should have been -0.5. So if we now do that again, hello world, we get a 2x2 all 0 matrix. So everything's been correct, and you can see if we didn't do this cursory check, and honestly I didn't plan it, I just made that typo, then when we ran the program, a very large program perhaps at the very end of what we were doing, we would have had a considerable amount of difficulty pinning down what it is that actually went wrong in there. Okay, so we can now delete this little cursory check and continue with our coding. One other thing that needs to be defined before we start taking direct products for a 2-spin system is the unit matrix. So unit equals, as it should be, 1, 0, 0, 1, just a unit matrix. Okay. Now, because our system is a 2-spin system, we now need to define the spin operators for the 2-spin system. And that is done, as you remember, with Kronecker products. And we'll call the first spin L and the second spin S. And so the second stage is to calculate the 2 spin operators. Calculate 2 spin operators. Right, so if we call the first spin L, then Lx, the x operator for that spin, will be a Kronecker product, Kron, of sigma x on the first spin and unit matrix on the second one. Then similarly, Ly will be Kron, sigma y, unit, and so on will now continue. As you can imagine, these things are pretty easy to automate. If you're running an n-spin system, well, you'll just have to declare a for loop and loop over every spin, but it's a fairly simple calculation here, so I will do that all explicitly. Lz is Kron, sigma z unit, and similarly for the Sx, Sy and Sz, Sx is Kron unit on the first spin and then sigma x. Sy is Kron unit on the first spin and sigma y on the second spin, and Sz will be Kron unit on the first spin and sigma z on the second spin. Okay, in the same spirit as we did it for Pauli matrices, we now need to test these things, and I'll just run a couple of cursory checks here. So let's say Sx times Sy minus Sy times Sx minus I Sz should be 0. Then Lx times, let's say, Sz minus Sz times Lx should be 0, because the two operators that refer to different spins must commute. And let's test something for z. So let's say Lz crom Lx times Lx minus Lx times Lz should be equal to 1I Ly. Should it? Yes, it should. So we should get 3 matrices 4 by 4, all 0, as a result of running this function now. So I'll run it again, and there we are. We've got our 3 matrices, and all of them are 0, so everything seems to be correct. Now, as you can see, it's a fairly orderly code so far. What I usually do when I'm coding spinach is I group things of similar types around similar lines. Typically there's plenty of horizontal space on people's screen, but not a lot of vertical space, so for reasons of prettiness it is preferable to do things this way. Okay, so we've created our basic operators. Now, because Kronecker product commutes with plane products, it doesn't make any difference whether we compute 2 spin operators. So let's say Lx Sx, a Kronecker product. We could do it with crom sigma x and then sigma x. That will be a 2 spin operator, or we can use the operators we've already created. We can just take Lx times Sx, and if we did everything correctly now, that should give us the same answer. And again, it is a good idea to just check that it does give us the same answer before proceeding with this. There we are. Indeed, the answers are the same. So let's delete this checking and proceed with our business of writing this code. Right, we have defined the basic operators, so the infrastructure, as it were, is built. So what we now need to define is the Hamiltonian. So build the Hamiltonian. And well, here comes the liberty. We can, let's say, set up some pretty basic NMR calculation, pulsar quark. In a pulsar quark experiment, what we have is our rotating frame Hamiltonian, which includes 2 kinds of terms, the Zeeman terms and the J-coupling terms. And the Zeeman terms are the interactions between the spins and the magnetic field. So let us say omega L, the Zeeman offset frequency of spin L, will be, let's say, 200 Hertz. And because it has in magnetic resonance simulations has to be in angular frequencies, that will be 2 times pi times 200 Hertz. And it's a good idea to let your future users know what this is. This is 200 Hertz offset frequency for spin L. Similarly, omega S would be 2 times pi, let's say 500. That will be 500 Hertz offset frequency for spin S. You see, we don't just put random numbers in without any comment. We know that these parameters are the ones we've chosen, we note that in the code, and then we give a descriptive name to it. So omega L, if you read a typical textbook, would be the actual notation for that frequency for spin L. And then J, let's say, will be pi times, well, 40. And the reason it's not 2 pi but just pi is historical. You see, J coupling, when you measure it in the spectrum, is not measured from the middle of the multiplet to the peak, it's measured between the peaks. So as it were, the J coupling that we measure from the data and the J coupling that's typically reported in the literature is twice the actual coupling, and so when we put it into the Hamiltonian from the literature, it has to be just pi. It's an important thing to note because, well, this is one of those historical conventions, and they just have to be obeyed. Right, so that will be a 40 Hertz scalar coupling. Between the two spins. And we'll just put it in there. Okay, so we can now put the Hamiltonian together. H equals omega L times Lz plus omega S times Sz plus J times the scalar coupling operator. And the scalar coupling, as you remember, is Lx times Sx plus Ly times Sy plus Lz times Sz. And that will be our Hamiltonian. Right, the Hamiltonian has been built. What we now need is the initial condition. Initial state. And well, if it's a pulse acquire experiment, then we start from the magnetization that was just sitting there on the z-axis. So rho equals Lz plus Sz. Both spins on the z-axis. Okay, so we now have the initial state and we now have the Hamiltonian. What we need is also the pulse operators. But well, the pulse operators we really already have. They are here, already defined. So what we now need to proceed to is to build the propagators. They will be the matrix exponentials that actually affect the changes that we need to make to the system. Now we need two kinds of propagators. One is the pulse propagator, the one that applies a pulse to the system, and the second kind is the evolution propagator, the one under which the system will evolve. So next stage here is to build propagators. Now the pulse propagator, so let's say P pulse, will be, well, as you know, it's a matrix exponential, so xpm in MATLAB, and it's minus 1i times the Hamiltonian. And if it's a pulse, let's say it will be a pulse on the y-axis, so it will be y plus sy, because we are pulsing both spins at the same time, times the duration of the pulse. Now, there's an interesting moment here for the pulses. You see, we can make a pulse at various different powers, depending on what the power of the hardware that's actually pulsing is. And if we need a given power, then we'll need a specific length, so that the totality is, let's say, a 90 degrees pulse. But the power and the time, they occur in a reciprocal relation. So if we just put here a pi by 2, what will happen is the pulse will actually be a pi half pulse, because really no matter which particular duration and which particular power we choose, duration over power for a pi by 2 pulse is just pi by 2. So a quick shortcut for a hard pulse that gives a specific flip angle. It's important that it's a hard pulse, so there's no evolution that's occurring inside it, save for that same pulse. It's a shorthand to get that pulse out. Okay, so that's the pulse propagator. Now we need the propagator for the evolution. P evolution, and that will also be an xpm minus 1i times our Hamiltonian times the time step. And we do not yet know what our time step is going to be, because really it does depend on the scale and the frequency of the processes that occur inside the system. And well, usually it's a Larmor condition. What we do is we take the biggest frequency in the system and we step at twice the frequency in order to digitize things correctly. If you remember it from the first term, we have to have at least 2 points per period of the fastest oscillation found in the system. So before we decide the time step, we actually need to find out what the fastest oscillation is, and it just happens to be equal to the norm of the Hamiltonian. The infinity norm of the Hamiltonian is a bound on the highest frequency it has, and the Frobenius norm is in fact the highest frequency that it has. So to be clear here, let's just take the infinity norm of the Hamiltonian and use 1 over that number as the time step. So time step will be 1 over the norm of our Hamiltonian. Okay, so we now have the time step, and we now have the 2 propagators and the initial condition. What we have to proceed to now is the actual simulation. But before we simulate, we have to decide what it is we are detecting. And typically what we will be detecting is some magnetization on the x and the y axis. So before we build our propagators, we get the detection state. So coil operator will be Lx plus Sx. And I'll just put quadrature detection straight in. We could have projected magnetization on the x, then projected it on the y, then taken the x plus iy to get the complex signal. What I'll do is something that I guess will puzzle some philosophers. I will detect using a non-Hermitian operator, namely this one, Ly plus Sy. So because this is a non-Hermitian operator, it's the plus operator in fact, the observable will be complex, but the resulting complex observable will be exactly equal to the quadrature detected signal. And we wouldn't have to have all the linear combinations at the detection state, because we already are detecting with quadrature and are already making the complex signal that can go straight into the Fourier transform. So the justification for having a non-Hermitian observable is fairly complicated, but you can see that, perhaps contrary to the history of quantum mechanics, in magnetic resonance we do fairly often effectively detect non-Hermitian operators. Right, so simulation. Stage 1. Pulse. So rho equals, if you remember the equations that we had in there, it had to be the propagator or the pulse, the matrix exponential on one side, times rho, and then the complex conjugate, the Hermitian conjugate of our propagator, P pulse conjugate. The conjugation sign in MATLAB is fairly simple. So this is the standard two-sided propagation thing, and we've applied the pulse to our system. Now, what we have to do then is simulation, stage 2, evolution. So we have to take several steps, so n steps will be, let's say, 2048 to keep to the powers of 2. So that will be the number of steps in the simulation. So for loop n equals 1 to 2048. We have to detect the very first point, so detection comes first. So, well, FID M is detection, so trace of our detection state, coil. I made a typo here. Hermitian conjugate times rho. And that is the projection of our density matrix onto our detection state. Now, there is an interesting thing that is specific to MATLAB to an extent, and to most high-level languages. You see, it doesn't actually exactly know how many elements our FID would have until it fills them in. It's not sufficiently intelligent to figure out that we've got these 240,048 points. And every time it extends the array, it has to do a certain amount of memory manipulation, and it can be slow. So a good idea before we start filling in our FID is to actually initialize it, that is to fill it with zeros. So our FID array will be zeros with 2048 columns and 1 row. So that pre-allocates the array. And that would mean that next time it reassigns something, the array dimensions are already there, they are not being changed by the operation, and it is slightly faster from the perspective of the computer. Right, so we've detected our current state, so what we now have to do is to propagate it forward by a single time step. So then rho is our P evolution. Slightly long, too long a name here. P eval. Let's make it that way. Rho P eval conjugate, and that will be it. So end. So what will now happen is it will detect the magnetization in the current row, push the row forward by one single time step, detect it again, push it forward, detect it again, and so on. And of course, instead of the number, finally here we have to have n steps. And if the user ever wants to change the number of steps to a different number, he just has to change this variable, and it's given a descriptive name, so and commented, so it is understood by the user what actually is going on when that happens. Right, so, well, why don't we run this calculation and just write the FID to the console, just to make sure it's not producing anything silly. It should be a bunch of complex numbers, each of them of the order of 1 or thereabouts, and we just have to check that everything runs through smoothly, because if something is getting wrong at any of these stages, we better catch it now, rather than try to think through a much bigger program if we were ever to extend it to something else. Well, we'll have to Fourier transform things and plot them eventually. But okay, let's check whether we got everything correctly here by just running this program. Hello world, and indeed we have a bunch of complex numbers here, and those complex numbers look like they are the correct order of magnitude, and so it looks, at least at the moment, that we are doing things right. Secondly, what FID is really is an oscillation, so why don't we plot it? Why don't we plot the real and imaginary part of the FID? Plot real FID, and then plot the imaginary part as well. So hold on, so it doesn't overwrite the previous plot, and then plot imaginary part of the FID, and see whether the picture actually makes sense. So I'll run it now. Hello world, there we are. That's our picture of the real and the imaginary part, and as you can see, it does actually make perfect sense. This is the sort of oscillation that we would actually expect from our calculation. And you can see these bits, and they are approximately 40-ish hertz, so yeah, we're doing okay. it's at least some kind of oscillation of the sort that we are expecting. But of course the problem with this oscillation now is that it doesn't quite decay. Well, to be fair, it doesn't decay at all, because at the moment we only have Hermitian terms in the Hamiltonian, and the Hermitian terms yield unitary dynamics under the matrix exponentiation, and so what we simply have here is a non-decaying signal, which will Fourier transform alright, but it will have those wiggles and other nasty things which we should get rid of. So before we Fourier transform the FID, the next stage is to run the apodization. Apodization. Well, how to apodize things? Let's take an exponential apodization. So let's take our exponential function. So window function will be exp, so a decaying exponential minus, let's decay it to exp minus 5, so 5 times our effective t1. And I wouldn't actually give it any specific t1 here, I will just make the length of our trajectory equal to 5t1, or rather I will make our t1 adapt to the length of the trajectory. So times lin space, they're just numbers with linear spacing from 0 to 1, and 248 such numbers. So what this is a list of numbers which go from 0 to 1 in 2048 increments, then multiplied by minus 5, exponentiated. So let's see what we've got out of it. Plot window function. Just to take a look at what it is. Going back to our MATLAB window. Hello world. Undefined function or variable. Have I made some kind of typo? Yes. So back to MATLAB, and that's our decaying exponential, and you can see this is a pretty decent window function. You have to be careful with linspace, however, because what this did is it produced not a column vector of numbers, but a row vector of numbers. So if we actually look at it, so numbers of it, what MATLAB will print is a row. So we have to transpose it in order for it to match with the dimension of our FID. And finally, FID equals FID, then element by element multiplication by the window function. So what we should be getting now is a decaying FID. So if I plot real FID, that should be a nice decaying function which we can actually Fourier transform. So let's take a look. There we are. Well, this looks pretty. This is just like your ordinary FID should be looking like. And you see what I'm doing as I'm coding, I'm constantly checking what's going on. I've checked the Pauli matrices, I've checked the dimensions, I've checked the FID, I've checked the window function, I've checked the resulting FID. So it's much easier to catch errors that way, because they will inevitably happen. Every time I'm coding something, I'm making them in quantities. Typically every, let's say, 10 or 20 lines, there will be some show-stopping typo somewhere, and unless you are checking it all the time, it might actually be quite difficult to catch them afterwards. Right, so we've got our FID, and it sure looks in a good shape to be Fourier transformed. So let us Fourier transform it. Right. Next thing, Fourier transform. Spectrum is equal to FFT FID. Now, there's a peculiar thing about MATLAB in that it places the zero frequency not at the center of the spectrum, as we typically do in magnetic resonance. It places it at the edge of the spectrum. So left edge, and because it reflects periodically, right edge corresponds to the zero frequency. Not something that's conventional in NMR, so typically what we need to do is to shift that frequency into the center, and the command for that, obviously MATLAB realizes that some engineers prefer things in the center, is FFT shift. So we'll shift it to the center. And well, that's our spectrum. Let's try plotting it. Plot real spectrum and see what happens. Hello world, there we are. That's our doublet. But what do we see? We see a completely unexpected pattern of intensities in here. It should really be roofing in a completely different direction. So what's going on? And what's going on is poor digitization. You can see that we don't have enough points to properly digitize the top of this signal. And this is because we are digitizing it very close to Larmor frequency on the one hand, and second, our FID decays, but then we chop it off. We don't do zero filling. So why don't we now do the zero filling, which, as you know from our lectures, corresponds to harmonic interpolation of the spectrum. And in order to do zero filling, what we simply have to add here is the number of points. So why don't we zero fill it to, let's say, 8K, or maybe even 16K. So 8196 points. So with zero fill. And take a look at that spectrum again. So we'll close this window and do that. For a world, there we are. And now we are digitizing it properly, and we've got a nice, beautiful roofing effect from the strong J coupling. And that's just the number of points in the denominator. And that's the intensity, and of course the intensity means nothing in magnetic resonance. It's a function of the peak width. What really is conserved is the integral. Well, there we are. We can make a few things slightly prettier here. So let's say plotting. We could in principle create the axis for the plot for it to be in real seconds for the FID and in real hertz, or ppm for the spectrum. One particular thing that needs to be noted is the Fourier transform that MATLAB has here conforms to engineering conventions for Fourier transform. So watch out where your center frequency is, watch out where your positive and negative frequencies are, but other than that you can immediately recognize the spectrum that we all know and love, a two-spin system. What we can now do is, well, play around with it a little bit. We can put the J coupling not to 40 Hertz but maybe to 100 Hertz and rerun the thing, and of course the coupling increases. We could put the apodization up a little bit so it wouldn't be 5 but let's say 10, so the lines will get broader. There we are, they did. We can put the J coupling to some huge number, 400 Hertz, and then have various interesting things happening to it, or maybe even to 1000 Hertz, so it exceeds the line separation and you get this nearly forbidden transitions with low intensities here. We can have that J coupling 40 Hertz back, but put our frequencies equal, and as you know, spins with equal frequencies do not show any J splitting, and if we run it again, indeed there is just a beautiful singlet of twice the intensity. But as soon as we make the frequencies even slightly different, the splitting returns and we get this classical strong coupling kind of roofing. We can experiment with various other things like Gaussian apodization. So let's say it's not an exponential, it's the exponential of that thing squared, so Lin spacing squared, and this will now be a Gaussian, and the signals should ideally be considerably sharper as a result. So element by element Gaussian here. So let's see what it plotted. Yep, you can see with Gaussian apodization the signal is very sharp indeed, no wings at all, and it's a perfect Gaussian. Here you can experiment with sync, we can experiment with no apodization at all, or let's just remove this square and put it -2 so we don't apodize it completely, so we'll now see sync wiggles. If we run it again, there, and you can see the artifacts of incomplete apodization here. So even this basic model can be quite interesting to explore, and it's certainly a great illustration to everything that you have in textbooks, and a great piece of practice, because trust me, by the time you've coded something like this yourself, you'll be through every single error, problem and fallacy that these things can possibly have. I guess this fairly neat piece of coding that we now have here is not very representative of how things are actually written in practice. It's just my 10 years of experience with writing the spinach library. I can sit down and draw something like that from scratch, and you see I've never hit any problems with signal phase. We've hit the real signal straight away, and we didn't have to worry about the quadrature detection because I knew, to put the complex detection state in here, and we didn't worry about where our frequencies end up because I knew to do the FFT shift, and we didn't have any reflections or foldovers because the time stepping has been carefully chosen and so on. But all these mistakes unfortunately have to be made to have practical experience. Let's actually experiment with the foldover. Let's change our time stepping to see what happens. I'll just put the apodization where it was, to -5, so we get our exponential back. And let's try and get our time step longer and longer and longer and see what happens to these signals. So if I take that time step we've declared here somewhere, time step, so it's now 1 over norm, so it's absolutely safe bet. Let's make it 2 over norm. Well, maybe 1.5, so we increase our time step by 50%, and so the range of frequencies that we can digitize at that sampling rate becomes smaller. So you see the signals moved a little bit to the edge, and if we make it not 1.5 but twice, so slightly longer, they move even closer to the edge. So this frequency here is those 400 Hertz, and we are sampling at the moment at about 400 Hertz. So let's see what would happen if we sample at the frequency that is not sufficient to properly digitize the spectrum. Bingo, the reflection. So it should have been here, and it went out of the range that has been properly digitized, and it reappeared from the other side of the spectrum, from here, and you can see the roofing pattern is the wrong way around, so this is the foldover that we have. So if we return it back to 1 over norm, so we get back our spectrum as it originally should have been. Okay, that's it for this practical, as it were. I've taken you from a blank page in MATLAB to a fairly functional, as you can see, simulation of a two-spin system. So the last thing to note here, before we wrap things, is if you want to extend it to 3-spin systems, then what you have to do is to declare third spin here. So let's say it will be mx and the corresponding cron. These crons would not just be sigma x unit, it would be sigma x unit unit. Then this cron will be unit sigma x unit, and this cron will be unit unit sigma x. So we have 3 spins, and therefore there should be 1 operator and 2 unit matrices into each of these. And then what you have to do is put your extra interactions here. So there will be omega L LZ plus omega S SZ plus omega M MZ. 2 more J couplings, the spins might be coupled. So another J with maybe a different numerical value, then Lx Mx if it's between L and M, or Sx Mx if it's between M and S. The initial state will have the extra operator here, Mz. The coil state will have to detect M as well. In principle, actually, if I only detect spin L, if I delete the S in here, what we will have in the output is just 1 peak. And you can see, interestingly, the rate transitions of the first spin at the second frequency. That is the consequence of having the J coupling there, because it mixes the energy levels. They are no longer unique for each spin, they are mixed. This is useful when we've got heteronuclear spin systems, because in heteronuclear ones you only detect, let's say, carbon and don't detect proton. SY, and we are back to the detection of the full 2-spin system. So if it's a 3-spin system, you add the third spin here, you add the third spin to the propagators. In principle, we could have only excited one spin here, so let's say our pulse only affects the first spin, and then if we run it, then we'll see again that only one spin has in this case been excited, second spin is not being excited and therefore isn't being observed, except for whatever got transferred across the J coupling. SY back to where we were. Norm is just a norm, Hamiltonian just a Hamiltonian, and everything else will be the same. So you see this beauty of MATLAB in that once you've declared a particular set of transformations, they operate on matrices of any dimension. So long as matrices are of consistent dimension, MATLAB will do it. So much of our simulation wouldn't actually depend on how many spins we've got in the system, assuming we've set up the matrices correctly on the outset here. Right, well, final thing before we wrap up is you noticed that I've edited quite a lot of things here. I decided maybe we want a 3-spin system, and maybe we want to detect something else, and maybe we want to pulse something else. And what that very quickly leads to is a peculiar kind of fatigue, in that you stop remembering what it is that you've changed in a particular instance of your code. And the only real remedy against it is something called the version tracking software, and I will briefly just show you what that is. Let's go to one of my directories in here where the spinach development happens, so work in progress, spinach, and you see these little signs, the ticks, the green ticks. This is something that the version tracking system puts. It says that nothing has been modified in this directory from the outset. So if we go, let's say, to kernel, and we look at the version tracking menu, show log, it shows everything that's ever been done to this directory. And the program's called Tortoise SVN. You can download it and have a play with it. You need an SVN server, again, Google it up and see how it works. And you see, Luke Edwards, the PhD student in my group, has made a change because he discovered some bug or inconvenience that he wanted to work around. And if we look at what this change actually was, it's a particular function in our Hilbert space module that has been modified, and if I look at the show changes, it will actually show me what has been modified and where, and Luke has added this paragraph to the function. So you see, it tells you everything about who changed what and when. And more importantly, if I go inside this kernel and I open some function and I edit something, if I edit a little number or just change 2 letters around and then save it, then what would happen is it will instantly light up. So this one's read-only, so it's actually protected. Well, let's edit it in MATLAB. Let's go to this editor, open it, go to our spinach directory, and edit some function in the kernel. So I'll remove the dot, put another dot in here, and save it. And completely forget about it, let's say. And then look at the thing. It instantly lit up. It says, aha, you've changed something here. And then when you try and look at what's been changed, diff, it shows you this little dot that you have changed. So with this system, it's not possible to ever make an accidental change. And if you decided you don't want to make that change, you say svn revert, and then it reverts to back to where it was. And if you refresh the directory, so get out of it and back in again, it should actually refresh it. It would maybe of its own. Where's the cleanup thing? Yeah. Refresh the overlays. No, it's a Windows bug. Anyway, sooner or later a green tick will appear in front of this to say that this hasn't been changed from its original versions that it remembers. And well, it takes a little bit of getting used to that version controlling system, but it really, at least in the Spinach development, well, saved our bacon, because the program's huge. Many people work at it at the same time, change things here and there, and you come back on, you know, Sunday morning and you look at what's been done through the week, and there's a huge number of change by a number of different people, and the only way to keep track of it is this versioning system. And it really helps. Maybe in a month you decide that what you've been doing is something that is not going very far, and you want to revert to the code version that's been there a month ago, and in this version control system that simply takes one click to do that. I can give you an example. Somebody just sent me an email asking how a particular version of Spinach works, and the version of Spinach that I've got here is of course something that we're continuously working on, but I would like to revert it to the version that the person has talked about. So update to revision, and let's say I would like to update to revision 10.24. That is the previous revision of Spinach that's currently online. And what it will do is it will just change everything to exactly how it was at that exact point in time. So when I'm talking to the user, I can actually see exactly what it is that he's having a difficulty with exactly the code that he's having at his desktop. And when I'm done with that, I just say update again to revision to the latest head revision here, and it updates to the latest versions that we are currently working on. And you can see we're hitting some access control issues here, but these are technicalities. At least it has reverted. I think it's access denied because the code is open somewhere else. So it is important really at the time when you are starting to develop a large software package to have this version control system on, otherwise the multiple changes that people are making to it quickly become insurmountable. Right, that's it for today, and I hope that's useful.